Justin Miller, Oxford College Physics here. We got ourselves some physics to do now, finally. Done a bunch of math and a bunch of review stuff. Let us actually start talking about some physics. So, in physics, we need to be able to discuss things. Discuss things about, well, the state of an object. And what we're going to focus our attention on right now is changes that the object undergoes. Changes such as changes in position, changes in how fast it's moving, and the rate at which those changes occur themselves. So this brings us to some nice quantities that we will heavily rely on throughout this course, and those are displacement, velocity, and acceleration. So what we want to do is formally define these, both with some words and mathematically, and then we can go on and do some more stuff with it. So we'll start off with displacement. Displacement is a vector quantity that measures an object's change in position in a particular direction. So ultimately, it's how far did it move from where it initially was, and in what direction did it move overall? So that's what we have for displacement. We have this for a displacement in the x direction. We write delta x hat. This is the displacement vector, and that's how we represent it, delta x hat. The x says, hey, you're working in the x direction. Delta means change in. So we've got change in x position is what this ultimately gives us. So notice there is a little vector hat here because we want to make sure that we're talking about a vector quantity. And how do we discuss this? Well, mathematically, this is just a change in position. So we can write this as x sub f minus x sub I hat. So what does this tell us? Well, x sub I is going to be the initial x position. And x sub f is the final x position. And I hat specifically tells us we're talking about the x direction. So it is somewhat redundant in this particular sort of format here. We've got an x here, where you say, well, duh, you're talking about the x direction. Just want to make sure we're treating this as a vector. So there's the vector identity right there, telling us, hey, there's a vector, delta x hat, x final minus x initial, final position minus initial position in the x direction. So that's it. How are we going to measure this? SI units are meters. We use a nice little lowercase m for it. So here's an example, right? Here's a nice, this is a 2-meter stick, 2 meters long. So there it is, 2 meters, I'm about 6 feet here, and hey, there you go. Anyways, I can be right here initially. So I've got my initial x position, and I'm gonna move over, I'm gonna call that the x direction. I move over to this position right here. And what can I say? Well, if I say that that's the positive x direction, and I just move 2 meters in the x direction, my displacement is 2 meters I hat. That's it. If I say that that's the positive x direction, which makes that the negative x direction, and I move from here to here, I just move 2 meters in the negative I hat direction, or my displacement is negative 2 meters I hat. Again, the negative sign goes with the direction. So this is how we treat displacements in one dimension, and we're just dealing with the x direction, but we could go ahead and say, well, what about the y? We have a delta y hat, or the z, delta z hat. We could really discuss any direction we want. Right now we're just focusing on one x direction. So that's it. So here's a question for you. Is there a difference between displacement and distance? And the answer is sometimes. It really depends. If I say I start here, this is the positive x direction, and I move 2 meters in the x direction, well, my displacement is 2 meters I hat. My distance that I moved is 2 meters. There's no I hat because it's just a scalar quantity. How far did I move? 2 meters. Okay, great. If I move from here back to there and say, well, that's the negative x direction now my displacement is negative 2 meters I hat, but the distance I moved is still just 2 meters. I don't want to call it negative 2 meters, I moved 2 meters. But here's something else. What happens if I go like this? I go ahead and I'm going to move 2 meters this way, then 2 meters this way, then 2 meters this way, then 2 meters this way. Here I am. Say, how far did I move? And what you should be able to say, you moved 2 meters, then 2 meters, then 2 meters, then 2 meters. You moved 8 meters overall. So yeah, that's right. That's the distance that I moved. If I ask you, what's my overall displacement? Well, my initial position and my final position are the same position. My displacement is 0. I haven't been displaced from where I originally was overall. So there's a pretty big difference in those numeric values, right? 8 meters versus 0 meters I hat. So that's something you got to be a little bit aware of and careful of with displacements is it has the direction associated with it. But other than that, that's that. So we'll get into delta y hats and delta r hats later on. Again, we're just sticking with the x direction right now. All right, so there's displacement. Pretty friendly, indeed. Now let's move on to velocity. Velocity. Velocity is the rate at which displacement is occurring with respect to time. Actually, we'll say the rate at which position changes with respect to time. Rate at which position changes with respect to time in a particular direction. All right, so there's a definition of velocity. It's how fast something's going in the particular direction that it's moving, or in a particular direction itself. So there's a couple different ways that we're going to deal with velocity. We can deal with an average velocity, or we can deal with an instantaneous velocity. So let us do this. Average velocity in the x direction. Again, just sticking with one dimension for right now, that dimension being the x dimension, is v sub x average hat. It's a lowercase v, I know it's capital, but it's hard to tell the difference. It's a little v, the hat on top of it, and I subscript it with an x, comma, AVE for average. The x is saying we're talking about the x direction, and average means that we're talking about just the average value of this. The average value of an object's velocity depends on the displacement that's occurred of the object under consideration divided by the time interval over which that displacement has occurred. That's it. Displacement over the time interval of that displacement for the average velocity. So what does this give us? Well, again, it gives us a vector that depends on the displacement, and then it's divided by time. So let's look at that. SI units are meters per second, which, we'll just do that. M divided by S, meters per second. Okay. So some things about average. An average may not really be how fast an object's moving. It could just be, well, again, an average value. There's something about averages that can correlate with constant values. And I could have that say, I move 2 meters in 2 seconds, let's say. But I start from rest, 1, 2. I move 2 meters in 2 seconds, but I wasn't moving at the same rate the entire time. I moved slow in the beginning, fast at the end. My total displacement over that 2 seconds was 2 meters I had. The total time was 2 seconds. So my average velocity would be 1 meter per second I had. 2 meters per second divided by 2 seconds, and I had direction, 1 meter per second I had. That's great. Well, again, that wasn't a constant velocity, but I could move at a constant rate. So I could start measuring my displacement when I'm right here and already be moving. And be moving at a nice constant rate, 2 seconds to get this 2 meter distance. Moving at a nice smooth rate, 2 meters per second. Excuse me, 1 meter per second. 2 meters in 2 seconds, moving at a constant rate. So constants and averages are ultimately defined the same way, and that's something that comes in a little bit handy from time to time. But nonetheless, this is just our average velocity. What we also want to be considerate of is instantaneous velocity. Which is actually how fast something's going at a particular moment in time and what direction it's moving at that moment in time. How fast and what direction an object is moving at a particular moment in time. So how are we going to get the actual speed and direction of the object? How fast, which way, at a given moment in time? Well, what we can start thinking about doing is taking the time interval here and shrinking it down towards 0, making the time interval over which we're computing an average to be very, very small. And as that time interval becomes very, very small, we approach what is known as the instantaneous velocity. So we can say it's ultimately gotten by taking the limit as delta x hat divided by t, as delta t goes to 0. And this would be b hat. Instantaneous velocity. It's gotten by considering that limit. So we'll take a little bit of a look at this in terms of shrinking time interval down, but ultimately, if you've taken some calculus, then you note that you can ultimately define the derivative out of this. If you haven't, it's not important, that's fine. It just really depends what we're doing. So, true definition of instantaneous velocity is the first time derivative of position. And that's it. So there you go with that. Anyways, that's what we have. And we want to keep on moving. So What else can we do with this? Well, we've also got ourselves acceleration here. Acceleration. Acceleration is characterized by a change in velocity that is occurring over time. So anytime there's some change in an object's velocity, there is an acceleration that accounts for that change. That's what acceleration does. Acceleration is a measure of the rate at which velocity changes with respect to time. And again, just like velocity, we could define average acceleration and instantaneous acceleration. So let's take a look at this. Let me just write the word average here. And let's stick with the x direction. Is a hat sub x sub average is, well, it's the rate at which velocity changes with respect to time. So if we're talking about an average, we look at delta v sub x divided by delta t. So this is how we define average acceleration. What do we need? Well, delta v sub x is going to be v sub x final minus v sub x initial I hat. It's the change in velocity that's occurred. So we need to know what is the final and initial velocities. These are not average values here. These are instantaneous values. How fast was it moving initially? How fast is it moving after some amount of time transpires? That allows us to find out what delta v hat is. So Vx final is the final velocity in the x direction. Vx initial equals the initial final velocity in the x direction. Then note that these are instantaneous. Instantaneous values here. So to truly define the average acceleration, we need to know specifically the initial and final instantaneous velocities. And then, well, delta t is some t final minus t initial, which is this, the final time minus the initial time. That correlates with the change in velocity that's taking place. So let's look at something else here. Come back over here. Say the SI units of average acceleration. Well, we've got the SI units of velocity is meters per second. And then we're dividing it by, well, time, which is seconds again. So we've got meters per second per second. So we can write this meters per second. Second. And the reason that I'm writing it like that right now is just to get an idea of what acceleration is really characterizing. How many meters per second you change your velocity every second? That's what acceleration is characterizing. Meters per second per second. Meters per second of a change in velocity per second. So if I go from moving at 1 meter per second to 5 meters per second, well, I have a change in velocity of 4 meters per second then, right? I've increased my velocity by 4 meters per second. And if I do that, say, in 2 seconds, then my average acceleration is going to be 4 meters per second divided by 2 seconds, which will be 2 meters per second per second. On average, every second that has gone by, I've increased my velocity by 2 meters per second in the direction that I'm moving. 2 seconds go by, 1 plus 2 is 3, plus 2 is 5. Go from 1 to 5 in 2 seconds. So again, that's what acceleration is characterizing. Generally, we don't write the units like this. We write them as meters per second squared. But it is meters per second per second. And that's what it's really, again, linked with. Meters per second, change in velocity per unit time per second. All right, so just like we had ourselves instantaneous velocity, we can also have instantaneous acceleration. Maybe something's not changing the rate of its velocity at a nice, even rate. Maybe it's varying in some very complex manner. Well, for that, we need to know what instantaneous acceleration is. Instantaneous acceleration is the actual acceleration of an object at a particular moment in time. So for instantaneous, we'll again still stick with the x direction, one-dimensional-wise. We just have ourselves a hat, and that is going to be gotten by taking the limit of delta v hat over delta t as delta t goes to 0. We start shrinking down the time interval to be very, very small, and we approach ourselves the instantaneous value. So truly, a sub x is defined as, again, those 3 hash marks mean equal to, but they also mean is a standard definition, or is the definition of. So a sub x is defined as the first time derivative of velocity, calculus-wise. And since we have that the first time derivative with respect to velocity, we've also got velocity is the first time derivative of position. So with v hat, that's v sub x, being equal to dx hat dt, we can also write that a hat is equal to, well, v is dx dt. We stick that in here, and we've got ourselves d squared x dt squared, second time derivative of acceleration. Again, if you're not in a calculus-based course, don't worry about derivatives. No big deal. This is for calculus-based courses only. Anyway, that's pretty much that. You can put is defined by. All right, so what we're going to do is start to utilize some of this stuff, and what I really want to do is look at some graphical representations of velocity and acceleration so that we can get a better idea of what it means to take the limit as t is approaching 0 to get to these instantaneous values versus just an average value between 2 arbitrary moments in time. All right, be right back, and we'll do just that. All right, so put a little hat on this. Just notice that I dropped that hat. He's proper here. And again, let's just look at some graphical representations. So let's make a little plot. little plot of position versus time. So I'm going to draw a nice little XY coordinate system here. We've got time here, we have position here, that'll be measured in meters, this will be measured in seconds, so we're using some SI units. And what we can do, we can go ahead and draw in some sort of function here. I'm not going to specifically write out what that function is, but we could have some sort of variance in an object's position with respect to time. And we'll just say that this object goes like this. So let me do a little bit more here and change this just slightly. Nice little dip in it. There. We'll take something like that. So we're going to start here. The origin here is our 0, 0 here. T equals 0. We're right there. And then what are we going to do? Well, we're going to start changing our position. So this is going to be the x direction. And we can put in some increments if we want. Maybe we say 5, 10, 15, 20, 25. 5, 10, 15, 20, 25 meters within reason. And we can go ahead and say like 2, 4, 6, 2, 4. Oh, 2 bunched up there, so it's like go here, 2, 4, 6, 8. So there's some seconds there, and we can start asking some questions, right? So what happens if I say, hey, what is the average velocity between t equals 0 and t equals 8? V sub x average between t equals 0 and t is equal to 8 seconds. Well, what do we do? Well, we know this, right? V sub x average is going to be equal to delta x hat divided by delta t. Well, we've got the times. What do we need to know? We need to know the positions. So we've got, again, delta x hat is equal to some x final minus x initial I hat. And what we need then is, what is x final and x initial? Well, we're starting here at t equals 0. So we say at t equals 0, x initial is equal to 0. That's when we start time. Our initial time, t equals 0. We're initially at the 0 meter mark. And then 8 seconds goes by. Well, at 8 seconds, we're here, which we could translate over here and say, hey, that's going to be, let's call that 22 meters. So at t is equal to 8 seconds, x final is equal to 22 meters. All right, so we've got some information here. This is going to be our t initial, this is going to be our t final, and thus we can start sticking it in for delta x hat and delta t, and get ourselves that v sub x average is going to be equal to, we've got 22 meters for final, minus 0 meters I hat direction for delta x, and then we've got 8 seconds minus 0 seconds for delta t, which gives us 22 divided by 8 2.75. 2.75 meters per second I hat. There is our average velocity in the x direction over that particular time interval. Oh, grab that. So let's see what that looks like graphically, right? So what do we have here? Well, we've got, there's t equals 8 seconds. Whoa. And then we've got, there's x equals 22 meters from here to here. And then we've got the time that goes from here to here. So I could draw that in, but that's just along the axis to here. What I could do is I could draw a nice straight line. It goes from where we start at the origin, right here, and see something that we get out of this. So I ask you this, what is the slope of this nice straight line? Well, we know slope is rise over run, correct? Yeah, that's what it is. What do we have for the rise? Rise is going to be 22 meters. 22 meters. And the run is going to be 8 seconds. What does that equal? That equals 2.75 meters per second. So the point with this is that the slope joining the two coordinates for the initial and final positions over that time interval is equivalent to the average velocity when we're looking at a position versus time curve. Delta x over delta t, delta x over delta t. We're working in the I hat direction, we throw a little I hat on there, and we've got ourselves the average velocity in the x direction. So that's one correlation that we want to get out of this. So that's where, again, these average values come in handy in looking at how fast will I have to move on average to get there. Well, what happens if we want to know what the average value is between some other time intervals? Like, let's say, between 0 and 4 seconds. There's 4 seconds, and we can go ahead and make ourselves another mark on here. I'm going to use red. I'll say, well, now we've got this. We're looking at the average velocity from going from our initial point to some position here at t equals 4 seconds. So v sub x average from t initial is equal to 0 to t final is equal to 4 seconds is equal to, oh, we need a delta x over delta t. Let's say that that is 12 meters right there. 12, 13, 14, 15, that seems reasonable over 4 seconds. So we've got 12, let's do this. Got that it is an x final minus an x initial I hat divided by a t final minus t initial, which is then going to be equal to 12 meters minus 0 meters I hat direction divided by 4 seconds minus 0 seconds. So we get ourselves 12 divided by 4, 3 meters per second I hat. So the average rate that we moved over the first 4 seconds was 3 meters per second. The average rate that we moved at over the first 8 seconds was 2.75 meters per second. That's telling us something. We got two different average values depending on the time interval which we calculated them. This is indicative of we don't have a constant velocity. The velocity is changing with respect to time. And that can kind of be seen by looking at this graphically. Depending on what point we want to get to, we've got different slopes from here to, say, here, or from here to here, or from here to here, or from here to here. all different slopes, thus we have all different averages, thus the instantaneous must be changing with respect to time. Otherwise, if it wasn't, we get the same everywhere. So there's one thing that we've got going on. There's some other things that we have too. We could have ourselves a negative average velocity. What happens if I say, what's the average velocity between t equals 4 and t equals 6 seconds? Well, if we go ahead and draw that in, go from t equals 4 to t equals 6, I've got this line. What's the slope of that line? Well, we've got this little triangle right there. We've got this is the rise, which is going to be going from higher to lower, and this is the run in time, 2 seconds. So what do we have? This is 2 seconds there, and then we've got final minus initial. If we go ahead and say that this is 5, 6, 7, 7.5, we'll say. 7.5 correlates with that, and that, again, that is a 12 there. So we go from the 12 meter mark down to the 7.5 meter mark over a time interval of 2 seconds. We would have for this, the x average is going to be equal to, well, we've got 12 minus 7.5 meters pi hat divided by 2 seconds. So what do we got there? 5.5 divided by 2 gives us, excuse me, it's not 12 divided by that. Sorry. This is final minus initial. It is 7.5 meters minus initial of 12 meters. Negative 5.5 divided by 2 gives us a negative 2.25 meters per second pi hat. Negative velocity, negative average velocity. Why? Because, well, I'm going from this x position to this x position is moving in the negative x direction. Thus there's a negative average velocity correlated with that particular time interval. So there's all sorts of different things with this. But the one thing that we can get out of this is also extract out instantaneous values by thinking about this. What happens if I start thinking about, say, 2 locations that are separated by a very, very small moment in time? Let's say I want to know what is the average velocity between t equals 2 and t equals 3. Well, it'd be equal to the slope of that line, right? And we could compute what that is based upon that being 5 and that being 2. We've got 3 divided by 3. We've got ourselves 1 meter per second. What happens if I shrink this down even farther? Well, I could say between 2 and 2.5 at the slope of that line. Say 2 and 2.25, 2 and 2.1, 2 and 2.00001. And what ends up happening is I shrink the time interval down to be very, very small. We have the instantaneous value is equivalent to the slope of the line tangent to that point. So instantaneous velocity is equal to the slope of the line. Tangent to point under consideration. On a position versus time graph. Just had enough of it. So that's the idea again. So again, for calculus people, that's equivalent to taking the derivative, right? Derivative and evaluating at a specific moment in time gives us the slope of the line tangent to that point. So that's it. But even for non-calculus, we can still consider shrinking down time intervals to be very, very small and getting a really good approximation of what the instantaneous value is at that moment in time. If not, well, the actual instantaneous value itself. All right, so that would be it for average velocities. And ultimately, it turns out the same sort of way for average accelerations versus instantaneous accelerations. If we've got ourselves a plot of the velocity versus time, we can look at how the velocity is varying with respect to time and look at the slope of the line between 2 points and define what the average acceleration is. And we can shrink down those 2 points in time to be very, very small and approach the instantaneous acceleration by having the line tangent, slope of the line tangent to the point under consideration on the velocity versus time graph. So it follows the same sort of characterization. All right, so at this point, what we're going to do is take a little look at a problem involving some average values and go from there. All right, it's been fun.